In this video, we are talking about isotopes and the average atomic mass for elements. These are the learning targets. In our previous video, we talked about the atom and how the atom is the smallest particle of matter. It is the smallest piece of matter. And we also talked about subatomic particles of the atom, protons, neutrons, electrons. We talked about how protons will tell you the identity of the element. And we talked about how protons and neutrons will give you the mass number of an atom. Now, did you know that each element actually has different types of atoms? These are isotopes. In nature, elements are found as a mixture of isotopes. For example, hydrogen has actually 3 types of atoms. Hydrogen 1, hydrogen 2, hydrogen 3. Carbon also has 3 different isotopes. Carbon 12, carbon 13, and carbon 14. Isotopes differ in mass. So because they differ in mass, they're going to have different neutrons. The more neutrons they have, the greater the mass. So isotopes are atoms that have the same number of protons but different number of neutrons. Now remember what happens if you change the number of protons. You change the identity of the atom. You're changing the element. So isotopes, they're the same element except that they have a different mass. Different mass, different neutrons. So even though that isotopes have a different mass and a different number of neutrons, isotopes essentially have the same chemical behavior, since behavior is determined by the number of electrons, which we will get to in a future video. Isotopes are written in one of 2 ways. One way is this notation here on your screen. The symbol, the element symbol, is represented by this X. Top left, for the A, we have the mass number, and then the bottom left, we have the atomic number. If you are given this kind of notation, you actually don't need your periodic table at all. All the information you need is right here in front of you on your paper on your screen. If anything, you might need your periodic table to look up the name of the element. Here's the second way that an isotope can be written. The name dash a number, and that number that's written is the mass number. So what is missing from this notation? It's the atomic number. So you do need your periodic table to figure out the atomic number of the element. So take out your periodic table and let's go through this example together. Keep in mind that an isotope, when it's written this way, we have the name and we have the mass number. What we don't have is the atomic number or the symbol. So let's find carbon on our periodic table. Carbon on our periodic table is number 6. So we need the atomic number to tell us what? To tell us the number of protons. So all of these isotopes will have the same atomic number, meaning the same number of protons. So let's go through carbon 12 first. So we have 6 protons. If you know protons, then you know the electrons. They have to be exactly the same. And then how do you get neutrons? You take the mass number minus the protons to get the neutrons, right? Because protons plus neutrons is equal to the mass number, which the mass number, again, is this dash number. It's this number. That's the mass number. So let's take a look at carbon 13. How many protons? Well, remember, it's the same element, so 6 protons. 6 protons means 6 electrons, but this time how many neutrons? 13 minus 6 is equal to 7. Now let's do carbon 14. Carbon 14, again, the same element, therefore 6 protons, 6 electrons to match the protons, and this time how many neutrons? 14 minus 6 is equal to 8. So again, if you look at this chart, what is different about these 3 atoms? It's the number of neutrons and the mass number. What is similar? It's the protons and the electrons. Let's do these examples together. The way that the first example is written is that we have the symbol of the element, we have the atomic number, and then we have the mass number. You don't need to look at your periodic table at all because all the information you need is written right here on the screen or on your paper. So what is the atomic number of Sc? Sc is scandium. The atomic number is 21. The mass number. The mass number is 45. So how do you get protons? Well, if you have the atomic number, then you know the number of protons, and a reminder is on the bottom of your screen. And how do we get neutrons? Mass number minus the protons is equal to 24 neutrons. And how do you get electrons? Well, electrons will equal the protons because remember, this is a neutral atom. Let's do the next one, gallium-60. Now again, what's missing from here? The atomic number is not stated. Remember that 60 is the mass number. So let's look at our periodic table and find gallium. Gallium is number 31, Ga. So gallium's atomic number is 31. We have the mass number, that's 60. We have 31 protons. We have 29 neutrons. 60 minus 31 is 29. And we also have 31 electrons. Go ahead and pause the video here and try to do argon 39 and zinc 65 on your own. Play the video when you're ready. So this is what you should have gotten for argon 39 and zinc 65. If you got it, that's great. Virtual high five. Now let's take a look at the mass number versus the atomic mass that's written on our periodic table. Now previously we learned that protons and neutrons is equal to mass number, and the mass number we know is a whole number. So then why this number? Why is it a decimal? This is called the average atomic mass. Now, where does it come from? Each isotope has a relative abundance and a mass, meaning relative abundance is also a percent abundance. So it's the percent of how much of that isotope exists in nature. So what does that mean? So let's take a look at these examples. Nickel, copper, and zinc. Let's take a look at copper first. It only has 2 isotopes. Okay? It has copper 63 and copper 65. These are the percent abundances of each isotope. So copper 63, you can see clearly there's more of copper 63 that just exists in nature, and copper 65 is maybe a third of this, right? And so there's more of copper 63 that exists, and when you average the two together, and when you average it, I'm not talking about adding it up and dividing by 2, you gotta actually take into consideration the percentages. You get an average atomic mass of 63.546, and this is the mass that's written on our periodic table. Okay? Notice that it is not a whole number. This is not the mass number that we're talking about. Mass number, again, comes from protons plus neutrons. Average atomic mass, or in other words, atomic mass, is coming from the mass of each isotope and its percent abundance. Let's take a look at zinc. Zinc has 1, 2, 3, 4, 5 isotopes. Okay? Zinc 64, zinc 66, zinc 68, zinc 67, and zinc 70. Well, which one is the most abundant? Well, if you look at the pie chart, zinc 64 is the most abundant by nature. Which one is the least abundant? Zinc 70. And notice the atomic mass, 65.38. Which number is it closest to? It's closest to, it's in between 64 and 66, right? And keep in mind that the most abundant isotope is 64, and then the next one is 66, so it makes sense that the average atomic mass of zinc is 65.38. So no matter where a sample of an element is obtained, the relative or percent abundance of each isotope is constant. So in a banana, which we eat because we want the potassium, 93.25% of potassium atoms have 20 neutrons, 6.7% has 22 neutrons, and 0.01% has 21 neutrons. So potassium has 3 different isotopes. In another banana, the percent abundance of potassium isotopes will still be the same. It's just how it is, by nature. So the atomic mass is the weighted average mass of the isotopes of the element. No element exists with only one possible isotope. So when we calculate the average atomic mass, we are considering the individual mass numbers of the isotopes and the percent abundance of each element. And the unit for the atomic mass is AMU, atomic mass unit. Let's take a look at chlorine as an example. Chlorine has two isotopes, chlorine 35 and chlorine 37. Chlorine 35 has a percent abundance of 75.77%. Chlorine 37 has an abundance of 24.23%. And when we try to calculate chlorine's atomic mass, what we do is we take the percent abundance, which, you can't use the percent, so we change it to a decimal, and you multiply by the mass of that isotope, and then you do it again. Okay, so you do it however many times you need to, however many isotopes it may have, and you add it together, and you get an average atomic mass of 35.453. Well, let's take a look at the periodic table to verify our answer. Here's chlorine. Chlorine's atomic mass is stated as 35.453. It's the same. And that's how we get the decimal number on our periodic table. So there really isn't an equation that you could use or memorize, but if I tried to put an equation together, this is what it would look like. The abundance times the mass of isotope 1 plus the abundance times the mass of isotope 2, and you would keep going if it had more isotopes. Now, if you look here, remember, you're not dividing by anything, okay? You're just, by looking at that percent abundance, you're considering that when you multiply the mass. So that's what the weighted average is. Now let's take a look at this example together. So silicon has 3 naturally occurring isotopes. Calculate the atomic mass of silicon. Now notice that silicon has 3 different isotopes, silicon 28, silicon 29, and silicon 30. Now the individual masses of each isotope is actually given to you, like the specific masses are given to you. And the percent abundances are also given. So in order to calculate the average atomic mass of silicon, we're actually going to use the specific mass that's given. Now, if these masses were not given, we would have just simply used the mass numbers that are given with the isotopes. So let's go ahead and set this up. We're going to take the mass of the first isotope and multiply by the relative abundance. So the relative abundance is really the percent that's taken out, and it's the decimal form. So 27.9769 times 0.9221. And we're going to do that for each isotope that we have. So we take the second isotope, the mass, times the relative abundance. And again, the mass of the third isotope times the relative abundance. Go ahead and put that in your calculator and see what you get. You should have gotten 28.0857 AMU. Now, how do you know how many numbers to put down? Remember significant digits, okay? So the percentages, we're not looking at the percentages for the significant digits. You are looking at the masses though, and so with the masses, we're looking at 6 significant digits, and we're multiplying each time. So really it's the 6 that we're worried about, because again, we're not thinking about significant digits with percentages. And then you add them up, and when you add them up, you're looking at the decimal place. So it really should be the 4th decimal place here, a total of 6 significant digits. So let's think about it. Does this answer make sense? We'll take a look at the percent abundances of each isotope. Which one is the most abundant? Silicon 28. In fact, it's 92%, right? And so does it make sense that the average atomic mass is closest to the isotope 28? Yes, it does. There's one more way to double check our work. We can look on the periodic table. So use your periodic table to find silicon, number 14, and what's the mass? The mass is 28.0855. That's pretty close. So we know we did a good job on that. Let's take a look at our second example. Lithium has two common isotopes. Lithium-6 has a mass of 6.015 AMU. Lithium-7 has a mass of 7.016. The average atomic mass that's written on our periodic table is 6.941. What is the percent abundance of the naturally occurring lithium-6 isotope? So how do we solve this problem? Well, we're going to use the system of equations to solve this problem. Let's label lithium-6 as X and lithium-7 as Y. And we're going to create an equation with this, right? We're going to take the mass of lithium-6, 6.015 X, because we want to know the percent abundance of that, plus 7.016 Y, which is the percent abundance of lithium-7, equals the average mass, 6.941. Well, what's the second equation that we're going to write down? Think about the percentages. What do they have to equal? We want it to equal 100%, right? So really we can say X plus Y is equal to 1. And we're going to rewrite this as Y equals 1 minus X. So let's plug it in. 6.015X plus 7.016 times 1 minus X is equal to 6.941. Go ahead and solve. What do you do next? This is algebra, right? You're going to distribute. So once you distribute, you're going to add and subtract, whatever you need to do, whatever math function you need to do. And then we divide and we get X is equal to 0.07493. Now keep in mind that this is the decimal form, so this is called the relative abundance, but what is the question asking for? It's asking for the percent abundance. So what do? We just multiply by 100 and we get 7.493%, and this is the percent abundance. Now let's talk about ions. An atom is an electrically neutral particle. We talked about atoms being neutral, no charge. We just talked about an isotope, which is an atom with different number of neutrons. An ion is an atom that gains or loses an electron. So again, atom is neutral. We can say neutral atom. If we're talking about isotopes, we're messing with the neutrons. And if we're talking about an ion, we're messing with the electrons. So let's see what happens when an atom gains or loses an electron. There's two types of ions, a cation and an anion. A cation is a positively charged atom that lost an electron. So let's take a look at the lithium atom. Lithium atom has 3 protons and it has 4 neutrons, and we're just counting the subatomic particles that's in the picture here. And a neutral lithium atom will have 3 electrons. So go ahead and draw those 3 electrons on your notes as well. The symbol for a neutral lithium atom is capital L, lowercase I. Now let's take a look at the lithium ion. Lithium ion has the same number of protons, 3, same number of neutrons, 4. But now the electrons, and I will tell you in this video if they gain or lose electrons. Later on you will know which elements will gain or lose and how many. But for now I'll tell you that the lithium atom will lose 1 electron. Okay, so a lithium atom loses 1 electron. If it loses 1 electron and it originally had 3, how many does it have now? It has 2. So go ahead and also draw 2 electrons around your atom there. Okay, and once it loses that electron, we now call it an ion, a lithium ion. Now a charge is written as positive or negative. Positive if it lost an electron, and it also comes with a number to tell us how many electrons it lost. So in this case, it lost 1 electron, so it's positive 1. Plus 1 is the charge. And the symbol becomes Li superscript 1 plus. So the symbol you notice, it now is written with the charge to tell us how many electrons it lost. An anion is a negatively charged atom that gained an electron. So let's take a look at the neutral fluorine atom. A neutral fluorine atom has 9 protons, 10 neutrons. And if it has 9 protons in a neutral fluorine atom, it will also have 9 electrons. And the symbol for fluorine is F, capital F. Now let's take a look at the fluorine ion. Fluorine ion still has the same amount of protons and same amount of neutrons. Now, a fluorine atom will gain 1 electron. So how many electrons will it have? If it had 9 and it gains 1, then it has 10 total electrons. So what's the charge? It gained an electron, therefore it's a negatively charged atom, and we're going to write 1 next to it because it gained 1 electron. So what's the symbol? Capital F, superscript, 1 minus. So let's try these together. The symbol for a potassium atom is capital K. When a potassium atom loses 1 electron, it has a charge of +1. So then the symbol for the potassium ion is K, 1 plus. The symbol for a calcium atom is capital C, lowercase a. If it loses 2 electrons, it has a charge of +2. Plus lost, 2, meaning 2 electrons. The symbol for the calcium ion is capital C, lowercase a, superscript 2 plus. The symbol for a chlorine atom is Cl. Chlorine atom will gain 1, so has a charge of -1. And the symbol for chlorine ion is now Cl1 minus. The symbol for a sulfur atom is capital S. If it gains 2, it's -2. And then the symbol is S2 minus. So let's take a look at these examples here. And we're going to need our periodic table to help us fill out the information. So let's take a look at the ion, and we know that it's an ion because of the positive and negative charge there. Okay? Remember, if it was neutral, there would be no charge at all. No positive, no negative charge at all. So let's find magnesium on our periodic table. So magnesium is number 12. Its atomic number is 12. If we know the atomic number, then we know the number of protons, which is 12. The mass number is given, so neutrons is mass number minus protons, so that's 12. And how many electrons? Don't say 12. So look at the symbol. It says 2 plus. What does a plus mean? It means that it lost. How many electrons did it lose? It lost 2. So instead of having 12 electrons, which it normally would, a neutral atom would, it actually has 10 because of that symbol 2 plus. How about the bromine ion? Let's find bromine on our periodic table. Bromine is number 35. So 35. And how do we get the mass number? Well, we know that the atomic number tells us the number of protons, and the number of protons is 35. And so protons plus neutrons, 35 plus 45 is 80. And how many electrons do we have? And again, don't say 35. We're not talking about a neutral atom. We're talking about an ion. And it's 1 minus. So what does minus mean? It gains an electron. And so instead of having 35, it now has 36. Let's take a look at scandium. And the way that it's written, we don't need to look at our periodic table, right? The atomic number is 21. The mass number is 45. It has 21 protons. It has 24 neutrons. And how many electrons does it have? And again, don't say 21. Look at the symbol. 3 plus. Plus means that it's going to lose the electrons. So how many will it lose? It will lose 3. So originally, yes, it would have 21 electrons. But if it lost 3, that means it now has 18 electrons. So I hope by the end of this video, you are able to distinguish between a neutral atom, an isotope, and an ion.